Hi, I'm Anfal Siddiqui, and today I'm going to talk about neXt-Ray, a deep learning model for abnormality detection on bone X-rays. So a little bit of background. Musculoskeletal conditions are the world's leading cause of disability, and diagnosing them requires a trained radiologist to examine a bone X-ray or radiograph. As the world population ages, there's going to be an increasing prevalence of these conditions, and it's definitely going to outpace the capacity of radiologists to diagnose them through examinations of bone X-rays, especially in developing countries. So what we want is a quick, cheap, and automated means of detecting abnormalities from bone X-rays, something a deep learning-based model can provide. Some prior work in this space done by the Stanford ML group in 2017 used an ensemble model using a DenseNet 169 architecture, and it matched radiologist performance on wrist and finger studies, but it was worse than radiologist performance in other areas of the body and overall. Some recent follow-ups have actually exceeded the performance of that Stanford baseline and radiologist performance, but they required ensemble models, making them computationally expensive, which limits their ability to be deployed in cheap offline devices in developing countries, something that we seek to address with our model. So we trained our model using the Mura dataset, which is made up of 40,000 of these multi-view bone x-rays, each of which was hand-labeled by a radiologist, and they come from several different regions of the body listed over here. Here's some samples from the Mura dataset. Here, we see a humerus study that is normal. And over here, we see a humerus study that is abnormal. And as you can see, it has this very evident fracture or breakage over here. Now our model architecture uses a ResNet 152. And we chose a residual network because they tend to be less memory intensive than dense nets. And we went with a single model approach because we wanted to emphasize efficient computation, efficient and inexpensive computation. Now we replace the final layer of the ResNet with a sequence of a dropout layer, a fully connected layer with one output, and a sigmoid nonlinearity. And we trained it using standard binary cross-entropy loss. Now the input to our model is a bone X-ray from the upper extremity, and it outputs the probability of abnormality. If the probability is greater than 0.5, it predicts the bone X-ray is abnormal. Here are some results from the evaluation of our model on the test set. We had an overall accuracy of 0.81, a sensitivity of 0.78, and an AUC score of 0.89. And here is the receiver operator characteristic curve. Our best performance was on humerus studies, while our worst performance was on forearms. Now comparing neXt-Ray to the Stanford baseline and radiologists on the Cohen-Kappa statistic, which measures the level of agreement with our model and the test set, found that neXt-Ray actually performs better than the Stanford baseline and radiologists on finger and humerus studies. But it performs worse than the Stanford baseline and radiologists on all other regions and overall. So in conclusion, and some next steps, neXt-Ray did make some improvements on the baseline, but overall it did not achieve radiologist level performance. The most successful follow-ups to the Stanford baseline made use of complex ensemble models. So it may just be that single model ResNets are just not complex enough in architecture for this task. That said, because neXt-Ray did make some improvements on the baseline, it shows some promise. Some natural next steps would be to try a better loss function or explore different architectures to see if we can improve upon the single model solutions. Thank you so much.